So, friends, welcome to lectures geomorphology, and today we are going to continue with the fluvial process and particularly the drainage analysis. So, if you remember our last class, we are talking about these channel habits, how different channel habits are formed with the change of grain size, slope, then channel width and water content, and finally, we found the channels which are narrow and deep are more efficient as compared to the channels which are wider and shallow. And the efficiency of a channel, it depends upon its hydraulic radius and which is a measure of its wetted perimeter and cross sectional area. So, remaining cross sectional area constant, if wetted perimeter varies, then the hydraulic radius varies, and those hydraulic radius, it is a major factor that defines how efficient the channel will be. So, today we will talk about this drainage analysis. What does it mean? What the drainage analysis says about this area, either it is related to lithology, related to slope, related to climate, related to tectonics and related to any other, suppose for example, alluvium, whether this alluvium which type of material is consist of, and what are these channel patterns and channel patterns found, and whether this channel pattern will remain as it is throughout its time span or it will change with time with a change in climate and tectonic scenario, and how this channel pattern will be interpreted to infer what lies inside, what structure, what lithology lies inside. So, drainage analysis, it is a useful tool for structural interpretation, particularly in area of low relief. Why the low relief and why not in high reliefs? So, why high relief areas, mostly the mountainous terrains, they are very rock terrains and drainage has to adjust themselves. So, here in the low lying areas, low relief areas where frequently change drainage, they are frequently change their positions and they are free to move, and these low relief areas generally mostly it is alluvium cover. For example, we take this example of Himalayan and the Ganga plain. The Ganga plain, it is a low relief area filled with alluvium. So, these are the alluvial channels, and those rivers which are coming out of these Himalayas. So, you will find their behavioral change at this Himalayan system as well as the same river or the same channel which was flowing at this Himalayan system or this Ganga plain system. So, this drainage analysis includes consideration of drainage pattern. Drainage pattern, that means what type of drainage pattern is it? Either it is a dendritic pattern, it is a trellis pattern, parallel, subparallel, there are many drainage patterns are there. So, it includes what is the drainage pattern. First, drainage analysis if you are asked to do. So, what are the different parameters you have to calculate, what basis you will calculate the drainage analysis, or what basis you will carry out this drainage analysis, it is mentioned here. So, first is drainage pattern, what is the different drainage patterns you are finding in this area. Then drainage texture, either it is a coarse texture or it is a fine texture, that means the drainage they are very, or channels they are very closely spaced or they are widely spaced. Then individual stream pattern, as we have already discussed, individual streams, either it is a straight channel, it is a meandering channel, it is a braided channel. So, individual stream pattern how they change. And drainage anomalies is very important in terms of deciphering the structural patterns inside. For example, if you see these figures are given here, these are this drainage pattern or this drainage anomalies from this Ganga plain, this 1, 2, 3, 4 photographs or through figures from this Ganga plain, and this fifth one it is from this coastal plains of Indian east coast. Now, you see, suppose for example, this Chambal river is flowing here, and you see there is a change in meanders, change in sinuosity of this river. Similarly, here there is a change in sinuosity of this. These are anomalies. So, that means within a straightness of the channel, or particularly if it is a straight channel, or within that, or a braided channel, within that you will find some exceptions. Similarly, here if you see there is a channel offset, and here if you see here there is channel offset is here, and there is converging of streams are there. That means, all this offset, this stream convergence, and this stream offset, they are coinciding in a single line. Similarly, here this drainage offset and this offset, they are falling on the single line. Similarly, along this line you are finding that some of these new streams are generated here. So, that means these are the drainage anomalies. By looking this drainage anomaly, we can predict what type of structures we are expecting in this particular area. So, this drainage anomaly has been successfully used in recent days in deciphering active dormant structures in this alluvial plains which are buried inside. So, though there is few anomalies that are found along this along a straight line or along a zone, they are very much useful to deciphering the tectonic activity in recently, particularly in the Ganga plains, how this drainage anomaly has been used to decipher the active faults. There are number of publications very recently this came out here. So, it may provide clues to inactive structures or structural features exposed at surface, to structural features currently rising, and possibly to buried structural features. So, mostly these drainage anomalies or drainage patterns, they are providing sufficient clues to find out what are the different structures, either it is inactive structures or active structures, and possibly buried structures. For particularly in the Ganga plain, if we talk about the buried structures, we have basement faults, several basement faults, they are lying kilometers distance, kilometers depth, but though they are lying kilometers depth, but still their activities, their movement along this fault, that affect the surfacial topography in the minor topographic variations is there, minor topographic relief variations is there, and these minor relief variations also that affect the drainage pattern and the drainage anomalies. But here you have to keep in mind that larger rivers like this Ganga, Yamuna, this Ghagra, Kosi, these larger rivers or any larger rivers, they respond very less to this topographic height or lows or these structures and compared to the smaller rivers of their area. Because smaller rivers, smaller channels, they have less capacity and less competency also, and this channel strength is very low as compared to larger rivers. So, that means in other words we can say they are less efficient than the larger rivers. So, for example, suppose there is half meter or 1 meter differential movement along a fault, these large rivers can cut through this differential elevations or the elevation difference and can readjust themselves with a few years or so. But at the same time, the smaller rivers which are cross cutting this elevation difference may readjust themselves by abandoned channels, by generating new streams, by converging streams like that. So, that means I want to say even the same scale of movement along a fault, the larger rivers respond less as compared to smaller rivers. So, that is why in the rivers and the alluvial plains, for analyzing the drainage anomalies, we have to be careful choosing the rivers. So, in Ganga plain particularly or the Himalayan terrain particularly, there are mountain fed river systems like the larger rivers which are fed from the snow, and they are perennial rivers, they are mountain fed river systems, and some of these rivers they are plain fed rivers, they are just originating from this plain, from this groundwater feed, and we have to analyze, if we want to analyze this region tectonically. So, we have to confine ourselves for the plain fed rivers because they are more responsible to detect the changes. So, changes can be detected very readily along this plain fed rivers as compared to the mountain fed rivers, because their capacity is more, they can adjust themselves by cross cutting these elevation differences. So, a drainage pattern is a design formed by this aggregate of drainage ways in an area. So, drainage ways, there are in which way this drainage is flowing, either it is straight way, there is a sinus way, there are cross cutting ways. So, these are these different type of drainage ways through which these channels are adjusted themselves, and finally, this defines the drainage way or the drainage patterns. A stream pattern is the design of the single drainage way. So, once we say a drainage way, that it in a drainage pattern, that means number of streams in that area, what is there, the overall drainage way has to be analyzed. But once we say stream pattern means here we are considering a single stream rather than more than one stream. So, stream pattern and drainage pattern are different. Stream pattern, we only consider only one stream, either it is a sinus stream, it is a straight, or it is a meander, it is a braided, like that. But drainage way, that means in an area number of streams are there, that means within a river system there may be one sub basin is there, some this, so that means that defines the drainage pattern. The drainage density is another measure of this drainage pattern calculation. So, drainage density provides information on the permeability and porosity on structure of this material and may infer this identity of materials. So, drainage density means how densely the drainage systems are arranged, how densely the streams are arranged. For example, if you see this figure, it is given. So, here this drainage area or this drainage basin is part of this Pranita Godavari valley. So, here this river, this is Andheri river, it separates two different lithologies, and this left side to you it is Gondwana sandstone, and the right side is granitic gneiss migmatite or the peninsular gneissic complex. So, now if you visually see this drainage pattern, this drainage distribution, this granitic gneiss migmatites, they are showing high drainage density as compared to these sandstones and the Gondwana sandstones at the left hand side and separated by a fault. So, this main reason behind it that the sandstone being porous and permeable, they can allow this water to percolate down, and that is why much of this water they percolate down and less are appearing as surface flow. However, these granitic gneiss migmatites, they are very hard, compact, non-porous, non-permeable. That is why this maximum drainage systems in this area, they are surface expressions of the streams rather than there is down percolation. That is why a drainage pattern that can give you overall idea what type of material lies beneath, irrespective of lithology, either it is porous or permeable, but there is no 100% measure from this laboratory, but you have to go to the field to define whether it is a granitic gneiss or it is a imporous, any other material is there. So, but in a laboratory an overall idea you can gain, either you are dealing with a sedimentary terrain or a metamorphic terrain or igneous terrain, and what is their overall topography, what is their overall slopes. So, that can be defined here. And in the left side of this system you will find this change of drainage system with time. So, for example, if you see here earlier, these are gently sloping sedimentary strata are there on which the streams are flowing here. So, now suppose for example, here a fault is growing. So, with time the fault they increases its length, and also these differences, the elevation differences, the throws increases, and finally a full fledged fault is developed. So, from here to here, these 4 figures, if you see here stage 1 to stage 4. So, you can say here this the stream earlier flowing here in a straight channel, with time its sinuosity increases, and finally this stream which was earlier flowing as a independent stream here, due to increase in sinuosity, due to increase in elevation difference, its strength is not enough to cross cut the elevation, and finally it has to move like this, it has to move in this way, and it is mixing here. So, that it is adjusting itself with the growing fault scenario. So, finally, this is the modified pattern of this drainage system earlier in geological past when these three independent streams are flowing, now you see these streams are not independent, instead they are merged together and finally forming a single stream. So, that means I want to say this drainage pattern in one area, it does not remain constant for its lifespan. So, with time, with changing tectonic scenario, with changing climatic scenario, this changing block tilting due to faulting or due to subsidence, this drainage pattern changes. That is why we are getting some paleo channels, that means these are the channels which through which this channel was flowing earlier, and now that they are finding in the abandoned form, and the channel has diverted its position. So, this is due to the tectonics, this climate effect or this local effect also, the local sedimentation effect also. So, that means by looking at drainage pattern we can say what type of scenario we are going to deal with. So, here from this area I have collected some data. This is from granitic gneiss migmatite and this is Gondwana sandstone. In between we have a sedimentary patch which is mostly representing the neoproterozoics or the proterozoic sedimentary rocks. And by calculating the drainage parameters in these three different localities, we can find out what are these changes, how the lithology is changing this, how slope and lithology they are influencing the drainage parameters. For example, if you see this bar diagrams that is showing the stream frequency, infiltration number, drainage density, bifurcation ratio of different streams of this overall area, and this is Gondwana sandstone, it is Phanerozoic, and here in between there is a limestone patch which is highly fractured because it is a fault zone which is fractured, highly fractured, and the fracture planes they are filled with hydrothermal fluid like calcite, like quartz, veins are there. And this side is granitic gneiss migmatites, and if you see here this is topsoil, that means it is a highly weathered soil is there, and if you see here this is the granitic gneiss migmatites and what is called the peninsular gneiss, and here the soil development is there, this much thick soil development is there. And this A, this representing this photograph, it is from Gondwana sandstone, and here B, it is the limestone. You see this limestone they are highly fractured and filled with quartz and calcite veins, and this is C, this is the pluvial sandstone, again it is fractured and it is filled with quartz veins. And here this same region there is another photograph, you see there are cross cutting relationship of quartz veins, and that means I want to say though it is a sandstone, it is porous and permeable, but this porosity and permeability has decreased significantly due to this hydrothermal fluid emplacement. And here though it is granitic gneiss and migmatite, but this top part, this top soil it is highly weathered, and that is why if you see this drainage characteristics and here the drainage characteristics they are looking similar, but not same. But overall if you are moving from this area where this top soil is not there or soil is absent, so this is totally non-porous and non-permeable. So, that is why in the previous figure we are showing there is a high drainage density is there, but in particular area this is showing this high soil development is there. So, that this drainage anomaly or the drainage parameters here and here both are assuming to be same or looking same, but in between as it is hydrothermal fluid is emplaced here, this porosity and permeability has totally gone 0, and that is why you see this drainage parameter infiltration number is abruptly increasing in this region. So, that means I want to say this medium porosity and permeability, this lithology in important terms that defines what type of drainage structure will be there, what type of drainage pattern will be there. So, drainage patterns generally are subdivided into two types, one is called basic type and is modified basic type. Basic types means by looking at drainage pattern, in appearance comes in your mind that this is a parallel pattern, this is a dendritic pattern like that, these are called the basic types. And modified basic type means within that basic type there are local change. For example, suppose there is drainage patterns, for example, here if you see these are, this is representing overall it is a dendritic drainage pattern. But if you see here these streams, these streams, these streams, they are showing parallelism. That means within the drainage pattern, within this dendritic system we have local parallelism, that means parallel drainage. So, this is sub basic types. So, basic types, that means overall we can say by looking at drainage pattern how it looks like, what is the first appearance is there, that is basic type, and within that if some subdivisions is there, that is called this modified basic types. So, a basic pattern is one whose gross characteristics really distinguish it from other basic patterns. So, that means by looking different drainage pattern we can say it is a drainage pattern, it is a dendritic pattern, that is parallel pattern, that is trellis pattern, rectangular pattern, annular pattern. So, these are the basic patterns of drainage patterns. But modified basic patterns differs from these type patterns in some fairly obvious regional aspects, as for example, the tendency towards parallelism of these larger tributaries in a dendritic pattern. So, that is modified basics. So, both modified basics and basic patterns, they define the drainage pattern of an area. So, there are some drainage pattern which is called transitional. So, neither with associated with or neither it is fully indicating a particular types of basics. That means these transition type that are more important in terms of tectonics and climatic changes, because they are transferring from one pattern to another pattern. So, that means their dynamic system is there, tectonically more active areas, generally they show this type of transitional type of drainage patterns. So, the change towards parallelism might result from progressive steepening of slope. So, steepening of slope it due to upliftment. For example, here if you see, suppose this fault is growing and a block is uplifting. So, a drainage pattern which was earlier representing by this dendritic pattern, that may change, and with time within this dendritic pattern we may develop some parallel pattern. So, this is due to tectonic upliftment, increasing of slope. Similarly, trellis pattern or trellis characteristics may appear in dendritic pattern as streams are superposed from an overlying cover into the dipping rocks. So, that means here you see this is a dipping rocks of different rock types, and its expression if it is expressed in the surface. So, there will be parallel drainage patterns will be developed. So, that means I want to say a particular drainage pattern in a particular area that will define or that can give you clues in what type of structure lies beneath, what type of lithology lies beneath, whether it is a tectonically stable area or not, whether this climatic change has affect this drainage pattern or not. Obviously, the tectonics and climates that combinedly or independently they affect the drainage pattern of area. So, by analyzing subsequent time series data, that means within a time series, within a satellite imagery or in the toposheets within different time interval, if we analyze this drainage pattern, we compare the drainage pattern, we can detect these changes, and that change detection can overall lead to study the tectonic scenario or the changing tectonic scenario or tectonic climatic scenario of an area, or changing sediment production, sediment capacity of a stream, and sediment overall sediment production of an area. So, a complex drainage pattern, a complex pattern consists of two contemporaneous patterns adjacent to each other. So, that is called complex pattern, that means once adjacent to each other means it is called two contemporaneous, that means at the same times we are in one region we can develop a drainage pattern which is dendritic, and the other side it is parallel. So, that means we can say it is a complex pattern of drainage. And compound pattern, it consists of two unlike superimposed pattern, superimposed, that means here suppose one is your dendritic pattern and superimposed pattern is your parallel patterns. So, you can say it is the compound pattern of drainage, and the palimpsest pattern that consists of two superimposed pattern, but one is a paleo pattern. So, two superimposed pattern is there, but one is paleo, that means that is change had taken place. So, here the compound pattern and palimpsest pattern they are both similar, however, one is active, another is inactive. That means, in palimpsest pattern one is the dead type of drainage pattern and other type of drainage pattern is active, which is superimposed on it. So, drainage texture depends upon a variety of factors. In any one small areas where all other factors are constant, drainage texture may provide information on underlying material and indirectly on structures. So, for example, if you see this is a figure, it is indicating this side, this is fine drainage pattern, that means minute drainage, small streams, but large number are here. But here the streams are sparsely spaced, larger streams, longer streams, that means it is indicating a sloping surface, parallel patterns are there. So, parallel pattern, that means a long reading slope, a long standing slope is there. So, parallel drainage systems is there, drainage systems has been developed. Similarly, drainage anomalies are local deviation from drainage and stream patterns. So, drainage anomalies are there. So, as we have discussed, anomalies, that means it is an exception in a streams. For example, here if you see here, this is an exception. You see overall this channel is flowing and there is an exceptional high sinuosity is there, exceptional high sinuosity is there. Similarly, here channel offset is there, here channel offset are there. So, that means these are the drainage anomalies. So, drainage texture, drainage anomalies, drainage pattern that define what type of lithology, what type of structure, what type of tectonic scenario through which these channels are passing through. And analysis of drainage anomalies have revealed structural data in some plane and where other methods of investigation have been unsatisfactory. For example, if you see here, this is a satellite imagery of Haryana, and you see after a heavy rain you will find these channels, they are filled with water, and you see maximum of these channels they are abrupting here, they are abruptly ending here, this abruptly ending here. So, that means this type of photograph, or particularly this photograph was very useful to identify to the Jind fault, and these are the paleo channels, that means all these channels they are ending here. So, there was elevation difference, and due to this faulting activity the channels were abandoned, and after a heavy rain it was filled with water, and their satellite imagery was taken at that time, which is indicating that all the channels they are abruptly ending at this particular structure. So, that means this type of drainage analysis that will lead to identify what type of structures lies beneath, which is buried structure. Particularly this type of drainage anomalies or this type of drainage pattern or analysis, they are useful in plain areas rather than in a highly elevated area of the mountainous region. Similarly, this is overall drainage pattern of the Ganga plain, and part of this Ganga plain here river Ghagra and river Kosi is there. Within that you will find, if you see here mostly the drainage pattern are parallel to subparallel, and this is due to this higher slope, and here also we have parallel to subparallel drainage patterns are there, and at these pediment areas you will find this parallel to subparallel drainage pattern, but overall if you see here mostly it is finding, it is looking the overall it is a dendritic drainage pattern. So, that means I want to summarize is here and conclude is here the drainage pattern, drainage anomalies, drainage texture that defines what type of structures lies beneath, and how we can finally analyze and these drainage patterns, and it will detect this type of active and active dead or dormant structures. So, I think we should stop here and we will meet in the next class. Thank you.